Okay, let's do this. So today, today we're going to do most of Learning Objective 2. This is most of what you need to do for this objective. Friday we're going to finish up the and tokens part, which admittedly isn't too complex. Like coding it up is a little bit of work, but it's stuff that you've done before. It's generating the token and storing it in the database. And I don't have too many slides on it, but today is the bulk of Learning Objective 2, Authentication. How are we going to authenticate users? So after today, Learning Objective 2 is mostly on the table. You just won't be issuing tokens quite yet, unless you look ahead and read those slides. And then it's on to the application objectives, which honestly a lot of these kind of come along just with authentication. With the exception of application objective 3, this one will be its own topic that we'll have to talk quite a bit about next week. We got a lot to say about that one. This is kind of like WebRTC in a way, in the sense that I have a lot to say in lecture, like a lot of background of how it works and everything. But when you go to actually code up HTTPS, it's not overwhelming of a task. It's not too bad. It's nothing like the AO3s of the last two assignments, where the AO3 was really the earn your A objective. This one isn't too bad, I don't think. I walk you through it. I give a live demo of everything you have to do. You'll be able to get through this one, not too bad. So let's learn what authentication is, shall we? So authentication. We want to authenticate users. Yay. So far, we haven't had any type of authentication, no user accounts or anything. And this is what we want. We want the feature of user accounts that you expect on today's internet, really, realistically. Even if you don't want to. There are a lot of sites where I visit where I just want to gain some information or something. It's like, hey, you have to log in. So even somewhat to a fault. But we expect this on the internet. So we're going to start treating users as users. We're going to get the kind of the illusion of persistence in our HTTP connections. 2 steps to this: registration and authentication. So you register an account, you log into an account. We're all used to this. I don't think I have to belabor the point of what these two things are. Register. During registration, you're going to provide a username and a password. And usually these days, you're going to provide your password twice just to reduce typos. For your homework, that's not a requirement. We're not going to bother with 2 password fields. You can if you want. I'm not going to stop you. But we're only going to require 1 password field. And then authentication, give me that same username and password again, and then you're logged in to the app. We've seen these all the time, and it's common for some authentication systems, some registration systems, I should say, to have you validate your email. So a lot of times you're going to verify that your email is a valid email. You'll register for an account. It'll say, hey, we just shot you over an email. Go check out that email first. And then the email has a link. You click the link, and then it says, okay, your email is verified. You're ready to use this account. You're all good to go. Or it locks down certain features until you verify your email. It's common as well. But a lot of times you have to verify your email as an additional part of this process. Again, we're not doing this on our homework or projects. Not required anyway. You're welcome to set this up. And maybe someday it'll be part of the course, email verifications. But this is common. And the reason why this is common is to combat fake accounts, bots, realistically, to make sure that there is at least some valid email address that somebody is using to be able to verify that there is something on the other end, not just a script that's randomly generating thousands of accounts. And this, I think I told this story this semester, so I'll tell the brief story of it. But I had a Q&A site in CSE 115 one semester, and I noticed there were tens of thousands of accounts being created. And it was certainly bots that were, it looks like it was SEO bots that were getting links to their customers' websites posted on my site. They couldn't post any messages, though, They would add their links in their user profiles, which were public to the internet. So they were still getting some SEO benefit out of it, is what it looks like. But they couldn't post anything on my site because I had email verification turned on. You had to get an email. It would send an email to your buffalo.edu email address. It would verify the domain, the buffalo.edu, email you, and then you'd click, yep, that's me, and then you would be able to post on the site. So they couldn't post any questions or answers to the site because, thankfully, I had email verification turned on, or else the entire site would have just turned into one big spam site, which would have been embarrassing at best. So email verification, even if you're not verifying the domain name, all those email addresses that those bots were creating were just blatantly fake, auto-generated. They had some method that was just auto-generating these email names for them, all just fake email addresses. So they wouldn't be able to verify those things anyway, which I suppose they could have their own email server and then eventually get their domain blacklisted and things like that, or banned from the site. So they could do things like that, but it's one extra step that they would have to take at the very least. And if you do verify the domain and say you have to be of this certain domain, email address at this domain, then you have some pretty good protection. Yeah.
If you have like a server that you own, do you repurpose it to be an email server?
You install an email. I forget the details. I wanted to look into this for a separate project, but I haven't refreshed my memory on it. But you just download the software to run an email server, and then it's an email server. There are extra steps you would take to have more usability and better features and stuff. But I have sites that will send auto-generated emails. I just install the software, and then it was Python for the one I'm thinking of. In Python, I install a library to interact with that software, just like you're interacting with your database service, and then tell it to shoot off an email, and then send it. Fun fact, you just choose the from email address. I can just send an email and say, this is from whoever, and it just sends it. It won't be verified, so it'll usually go in your spam, thankfully, that people can't just do that. But so our email clients are smart enough to say that, hey, I can't verify that was the person who sent that. But you just choose who that email looks like it came from. So that's the reason it's common to validate your email addresses. Make sure somebody's on the other end. To an extent, having a script that auto-generates email addresses can be done, but more tedious, tougher to do. Oh, I was going to be on that slide while I said that. So for authentication to the user, we're all familiar with that. We know how that works. You provide username and password, and then when you want to register, and then when you want to authenticate, you send username and password again. What we want to talk about in this class is, what does the server do? What's happening server-side to make all that stuff work? So, and you can fairly guess. Like, it's not overly complicated. We will make it overly complicated, don't you worry. But it's just not overly complicated on the surface. You take their username and password when they register, you slam that in a database, and then when somebody tries to log in, you take the username that they're claiming to be, you go to the database, you pull their password, and you check if the passwords match. If they match, authenticated, cool. If they don't match, not authenticated, get out of here. It's a failed login attempt. On the surface, that's what has to happen, but there's a huge implication here, is that you've got a database sitting there filled with usernames and passwords. What a lucrative target for an attacker to get a hold of. Now, presumably, hopefully everything works right. Attackers can't access that database. But if you have some SQL injection attack that can get in, if you have any attack that can get into your server and access that information, they have everybody's username and password, which is not a target that we're willing to store. You should never store a database with usernames and passwords, at least passwords in plain text. And you've probably at the very least heard that before. Hopefully you've heard that at this point, at some point in your travels or whatever, that never store passwords in plain text. That's what we want to talk about today. That's the big thing we want to talk about, how to securely store those passwords. How do you protect against SQL injection attacks? The one big thing we've talked about is using prepared statements. Beyond that, it's just outside the scope of my knowledge. But prepared statements will get rid of just about any SQL injection attack, except, I hear rumors that there are very sophisticated attacks that can get through that in certain cases, but really more advanced stuff. I've been using MongoDB, so I never got the chance to test it out. MongoDB there's no MongoDB injection attacks unless you're using a client library to connect to your MongoDB app, and the library itself has vulnerabilities. And so if you search online, my professor said MongoDB injection attacks don't exist, and some snarky article says, there was this case in 2015 where a MongoDB database had an injection attack launched on it. Your professor's full of crap. That's the library itself that was the vulnerability, not MongoDB. So there were some libraries that were released that did bad things. I'll leave it at that. It interpreted MongoDB queries as strings, like took a string and then parsed it as a MongoDB query, which is exactly the reason why SQL has that issue, is SQL statements are just strings, and then SQL parses the string as a SQL statement. MongoDB shouldn't have that issue because you're giving it an object. You're giving it this key value store that isn't interpreted or parsed as a string. So if somebody gives you MongoDB code as their value, it's just not going to do anything. It's just going to treat it as a value. MongoDB, you really don't have the same issue. With SQL injection, it's if you're not using prepared statements. If you use prepared statements, if you have question marks in your code, in your statements, it's a good sign you're doing the right thing. So we never store passwords as plain text, and we want to go quite a bit further than this. We don't want to say, it's only an issue if an attacker sends a SQL injection attack and, compromises the database and everything. No, we want to take this a step further. I want protection such that even the admins of the site themselves, like somebody has to have access to the database. At some point, humans are going to have access to the database. At the very least, the sysadmins, maybe the entire admin staff, the IT staff, possibly developers. Some places like to give developers access to the production database. People have opinions on that. It's controversial. I would say only if absolutely necessary, but even then, I don't know. Devs probably shouldn't have access to production data. But people are going to have access to this data. They're going to have access to the database. You don't want one IT personnel going, give me select star from the user's database. Now I have all the users. One employee at maybe Twitter's a strange target these days, but one employee at Twitter grabbing some celebrity's username and password and then masquerading as them, or selling that. I'm sure there's a black market where you can get some good money for that. We don't want anybody accessing these passwords. Nobody should be accessing these passwords if they recover the database. Anyone with access to the database shouldn't be able to get the passwords, and that's why we're going to use hashing. We're only going to store hashes of passwords. So like if you forget your UBIT password, you can't go to UBIT and say, hey, can you just write down my password real quick so I know it? They literally can't do that. They can't do that because nobody there knows your password. They do not know your password. That's the way we like it, and that's the way we're going to keep it. We like it that way. So we're going to do this by hashing. So what's a hash function? You've come across hash functions by now in your career. I know that because you took 250 with hash tables. But an overview, hash function is a function that's going to take some input and return an output with certain properties. So the hash functions used for hash tables are going to have some fixed length. If you have a hash table with 10,000 buckets, you want to make sure that the hash function outputs a value between 0 and 9,999. You want to make sure your hash function has that specific property. That's what we want from a hash function. And they're used for, as I just mentioned, hash tables, but they're not necessarily made for security purposes. This is a common misconception that I just like to dispel when I talk about hash functions. A hash function, if I have a hash function, that does not mean it has any security properties or privacy properties at all. If you take your hash function used to build your hash tables and hash your passwords with that hash function, you probably, most likely, don't gain any security properties from that, because that's not what that hash function is made for. It's not trying to hide any information. It's not used for that. Cryptographic hash functions are. So these are the hash functions we want to use to store passwords. These are meant to be one-way functions. They're hash functions designed to be one-way, which means it's easy to compute a value. Give me a value, I can compute the hash of it. Easy. Easy to do. You give me a hash of a value, and I can't go the other way. I can't produce the input that produced that hash. It's a one-way function is their purpose of existing. That's the reason why we want these cryptographic hash functions. And just despite what I said on this slide and the previous slide, just to confuse things, from here on forward, if I say hash function, I mean cryptographic hash function. So I'll add to the confusion too. But hash function doesn't mean cryptographic hash function in all cases. So if I have some password that is the literal string password, and I hash it using SHA-256, which is the hash function I'll talk about, this is the hash of that value, and then this is what's stored in the database. I'm going to store this hash in the database with the assumption that nobody can take this hash and compute the original password. At the beginning of the semester, I had no chairs down here, and then now I have an abundance of them, just starting a little chair farm. So nobody can take this hash and say, and compute, and being careful to use the word compute, and compute the input text of password. Now, you might just look at that hash and go, oh, yeah, that looks like the SHA-256 hash of password. You might actually be able to figure out that that's the hash for password, but you can't compute it. You can't write an algorithm and have a computer take that hash and quickly just say, oh, yeah, let me just run SHA-256 in reverse. Yep, that's the hash for password. Here's the input that generated that hash. That's what we can't do, or rather shouldn't be able to do. It's one of them things where we don't know. Nobody has publicly said, hey, I have a way to reverse SHA-256. Here's my algorithm. Here's how I do it. So it's one of them things where it's very possible. I shouldn't say very. It's minusculely possible that some hacker somewhere in a basement has some function they wrote that reverses SHA-256 hashes and just never told anybody and is using it to, wreak havoc somewhere or just do nothing. Maybe they just did it for fun. I don't know. But it's one of the things that's possible, but I'd say very, very unlikely. Somebody in the crypto community would have discovered it by now, possibly. I don't know. It's a tough thing to say. It's a tough thing to say for sure. There's a lot of just maybe it works involved in cryptography, as we're going to see over the next few weeks. There was a government site that I use when you request forgot password, it just sends you oh my God. There was a government site that I use that when we request forgot password, it just sends you an email with your password in plain text. Jeez. And unfortunately, the government could get away with it because what are you going to do? Use a different government? But yeah, they absolutely should not be doing that. You won't see that in the actual marketplace, that whenever there's fair competition, everybody's going to go to the other competition. You should go to the other competition. I already read that one. Yeah, that's awful. So we're going to talk about SHA-256. This hash algorithm is still used. They're constantly evolving, constantly coming out with new cryptographic hash functions that are better than the previous one, I guess. Like, for example, SHA-1 has some known vulnerabilities. There were some, at least theoretical attacks. There weren't attacks that really reversed the hash function in a super practical way, but there are some known vulnerabilities that have been published that make it, you shouldn't really use it for cryptographic purposes. We use it for the WebSocket handshake. Sure, we don't care if somebody reads that accept, and that's not the purpose of why we're using SHA at that point. So it's still part of the protocol, and there's no need to update it. But when we're storing passwords, we need a good hash function. SHA-256 is still fine. SHA-3, I believe, is starting to see use. But if you're using something like, I believe MD5 has been pretty much completely compromised, and there's a bunch of hash functions out there. This is the one I'll pick on. So if we go to this, I'm just going to go to this link. Yeah, open in Opera. Just open it. I don't care what you open it in. And if I do hello, compute hash, I'm going to get exactly that hash that we saw on the slides. At least I very well should. And if I go to this IntelliJ project that I happen to have open, and I'll paste that. I don't need this salt here. Paste that hash that I got from that website, and I'm going to run some Java code. So that website presumably using JavaScript to compute this hash, some JavaScript library. And I'm going to have this plain text of just the string password, one of the worst passwords you can have. And I'm going to compute the hash, which is going to use SHA-256. And because it's Java, I have all this gross overhead to compute one value. And I'm going to print it out. And once it finally runs, oh, of course it isn't. Because I'm base 64 encoding it. All right, well, I came this far, I have to do this. Why am I base 64 encoding it anyway? Byte array to string in Java. Oh, shoot. String dot. Give me a value of method. Oh. All right, I'm gonna table that. That one. Maybe we'll come back. My mind's gotta think about that.
Encode your answer and then compare the two.
You want me to base 64 encode it twice? No. I don't want to base 64 encode it at all. I just want the bytes. Here, let's. Let's do it this terrible way, because I can't think of a better way right now. String answer equals empty string. If this doesn't work, I'll give up on this. I won't spend too much time here. For byte b in hash answer plus equals string dot value of b. Return answer. Yeah, if this don't work, I'll give up. I didn't comment out my other return value. There's 100% a better way to do that, and we didn't get the right thing anyway. All right. Maybe I'll get that working for Friday, I guess. What should have happened is it's the same exact value that I get from this website. So SHA-256, the algorithm, is the SHA-256 algorithm. Like, that's what it is. It is what it is. No matter what implementation, what language, or whatever, SHA-256 is SHA-256. No matter what you're using, you're going to get the same output from the same input. So, I'm not going to go over the details of it because I always forget what they are. But the rough idea is that we have a bunch of XOR, a bunch of bitwise operations that we're going to use on the input, and then get some output after all these bitwise operations, and then feed that into the inputs again and just go through this several times. Since this is all bitwise operations, it's very fast to compute, but nobody's found a good, efficient way to reverse this process, to go through this backwards and get back to the original input. But it's a lot of bitwise operations and a lot of confusion, I guess, is just like mixing up the bits a whole bunch of ways, a whole bunch of different times. All right. So you can't compute the plain text input given the hash of a value, given just the hash, but that doesn't mean we're secure. Just because you hashed your value doesn't mean you're secure. And this is a surprisingly silly common misconception that I'm really sick of seeing. I hate seeing it every single time. I've seen this in peer-reviewed research papers where somebody's like, don't worry, bro, we hashed it. It's secure. Don't worry about it. That's not how it works. Just because you hash something doesn't mean it's secure. My evidence of this, my case in point is there are still password requirements. Why would there be password requirements if just hashing it was safe? Like if that was all it took. And one very easy attack is a brute force attack. Just try every possible password. So you can't go backwards. You can't take a hash and just compute what the input was, but you can use the hash function for its intended purpose. Just guess a password. If I think I know your password, if I think that you use the string password as your password, I'm going to take the hash function of SHA-256. The hash function is the function, no matter where, if I'm using it in Java and you used it in JavaScript, or I don't care. I know what the algorithm is. I'm going to pull up some library, and I'm going to feed it what I think your password might be. And if what it outputs matches your hash, I got your password. Yeah?
For that reason, we're just using the SHA-256 alternative.
Nope. So why not use a different hash function? So different sites are going to use different. They're not all going to be using SHA-256. It's just the one I'm using for this lecture example. So why not just use a different hash function? It's not going to add any security in a strict sense. This is what we call security through obscurity, where you're just kind of muddling up the waters and hoping nobody figures out what you're doing. So like I could use the SHA-256 hash function, but before I compute your hash, I add some characters. We're actually going to do something similar to this, so it's not the best example. But I could just add some characters to your password. You don't know what those random characters are. I only know what they are, and then I'm going to compute your hash. But eventually, over time, somebody's going to figure that out. What we want, or somebody's going to have access to the source code and figure that out. We want security where not even the devs or the sysadmins can hack us. They know exactly what to do. They know exactly what hash function is being used. So we wouldn't get that security at all. And eventually people are going to find out what we're using. Because you could home bake your own hash function that nobody's going to know. But eventually somebody can figure it out. If you're a lucrative enough target, somebody's going to figure it out. Even if they take the hash of their own password, they have a known input, known output, and then they try things until they figure out what you're doing. But we want the level of security where if somebody has access to the source code, which is common these days, how many of us use open source libraries? All of us, every one of us. We want to be able to use those libraries where the source is out there and known, especially for security. We're going to use known libraries for security instead of baking up our own hash functions. That code's out there, it's all known, and that's the level of security we want. We want to be able to use functions where everybody knows how it works, and they still can't hack us. That's our standard. That's the standard we have to have. It's the standard we should have, I should say. You should have that standard. Yeah.
But for the when Apple tells you that it is seeing your password in some database, does that mean your password's been reversed into SHA-256, or is it?
Wait, when Apple tells you your password's on the dark web? Wait, is Apple telling you that? Yeah. That might be spam. Don't click on those.
You can go to your stored passwords and it'll tell you security concerns. It'll go.
Oh. Okay. I'm not familiar with that exactly. I would guess that it's the hash, because Apple shouldn't know if it's your actual password. They should only be able to know if it's the hash. If they're on the up and up, which I would have to assume Apple is. Their reputation's at stake, so they're not going to risk that. I would have to think. How they fought against Congress to not get that backdoor in iPhones. So I would have to think, unless they did that just so I would think that, I don't know. But I haven't seen that specifically, but I would have to say it's the hashes. But once attackers have your hashes, they have, a lot of time to launch these brute force attacks. So if your password isn't super strong, they'll get you eventually. So to authenticate now, we don't say, okay, you gave me your username and password. Let me go to that user account for this username, pull up that password, and then check. What we're going to do instead is store the hash of the password, and then when we get a request for a login request, we're going to get the username, go to the database, look up the hash of the password, take the password that you gave us, hash that, and then check if the hashes match. If the hashes match, then we're good. And there is an implication here that if somebody's observing the login process, plain text passwords are still being handled during that process. It is going to be a plain text password at some point, and somebody can witness that and see it, but it won't persist in the database. It won't be stored as plain text. So whenever you hear that, it's always don't store plain text passwords, but that doesn't mean you're not handling plain text passwords. So there's still a potential vulnerability there. A rogue dev or even an incompetent dev, you have a logging system, you're logging everything, and you accidentally log the request, the login request, the HTTP request, the whole thing, and that request contains username and password, you can still have a vulnerability there. Is SHA-256 quantum safe? I'm not 100% sure. I don't think I've heard of a quantum algorithm that breaks SHA-256. I don't believe so, but I don't exactly keep up on all of that. I know RSA that we're going to talk about next week is definitely not quantum safe, but SHA-256 might be, I don't know. Is it, I missed the whole thing here. Is it possible, you're answering a question, never mind. Does that mean two identical passwords have the same output hash? Could that be a problem? Yeah, Vlad's answer is good here. Theoretically, yes. Since your SHA-256 hash outputs are fixed length, that means there's a finite number of hash values. So just by definition, there are inputs that are going to have, Vlad mentioned it too, the pigeonhole principle. There are going to be multiple passwords that hash to the same hash, but it's so unlikely. Like you have just as much chance of guessing the actual password than guessing a separate hash, or a separate input that computes to the same hash. That's what we call a hash collision. So it's not, you don't actually have to find out somebody's password. You just have to find something that hashes to the same value, which is super difficult. You're probably going to be better off finding their actual password because it's probably going to be easier to guess. By easier to guess, I mean it has less entropy. So entropy is a measure of uncertainty. In our purposes here, it's the number of guesses you have to make to guarantee that you get the correct output. The total number of guesses that you would have to make to get the right output. And this is usually measured by the length of your password. So if I have a one-character password, and you know that it's a one-character password, if I say, hey, if you watch me unlock my laptop and I hit one button, and you saw that I wasn't in the number row, I guess there's a lot of assumptions here, but you know that it's one lowercase letter, my entropy is 26, because in 26 guesses, you're going to guess it. Worst case, your 26th guess is the correct letter. If I have a two lowercase letter password, that's going to be 676 guesses that you have to make. The length of your password grows literally exponentially, which grows extremely fast. And if I mix in upper and lowercase letters, I'm up to 2704 already. And so this is the entropy, the total number of guesses, and we usually measure this as bits of entropy, which is this number, but log base 2, the log base 2 of this number. These numbers get out of hand and kind of ridiculous to wrap our heads around really quick. You're going to have these really long numbers. So taking the log base 2 of these just gets them into a realm where we can wrap our heads around them. Typically, 80 bits or more of security is our general rule of thumb in security, where we say if you have 80 bits of entropy, you're secure. You're good. You're good to go. So let's take a look at this. This part of my demo will work. he says confidently, hoping it won't crash and burn. But let's look at our encryption side. I'm not going to do encryption today, but I want to talk about bits of entropy. So I have this. So there's some code here which is going to take some bits of entropy, calculate bits of entropy, and then figure out how long it would take somebody to crack a password with that much entropy. So if I have an alphabet size, I'll leave this as 90. If I have an alphabet size of 90, and I have 8 characters, this is generally the password requirements. At least 8 characters, a mix of uppercase, lowercase, numbers, and special characters. It's like an alphabet of 90-ish. I did the math before, so I'll trust my math that it's 90 characters that are possible. And if you generate a 100% random string with 8 characters from those acceptable characters, what I want to do is compute the number of guesses, the total number of possibilities. Take the log base 2 of that so I can get the bits of entropy. And then I'm actually going to take the bits of entropy and exponentiate it again because I wrote this code weird. I'm going to raise that to the power of 2 to get the total number of possibilities. So I want to print out, where are we? I didn't put my main method as the last method, and it's trips me up every time I visit this code. You'd think I'd just move it. So I'm going to print out the total number of possibilities, the bits of entropy, and then this method years to crack, which is going to assume that an attacker can make this many guesses per second. So 1, 2, 3, so 1,000, million. Actually, let's leave it at 1 million right now. Let's give them 1 million guesses per second. So they have something that can compute 1 million SHA-256 hashes per second, generate the guess, compute the hash, and check if it's right 1 million times per second, which is absolutely reasonable. As you just saw, we'll jack it up a bit more. And then do a little math to figure out how many years that would take for them to crack. And let's run this thing. I'm moving it. You've tricked me for the last time. So if you follow the recommendations and you have 100% random, not a password that you came up with that is something that you can remember, but something 100% random from a password generator, you're going to get 51 bits of entropy. There's this many possible passwords that you can generate. And it's going to take that attacker 143 years to crack, which is, that's good, But if they have a little bit more power, let's make this 1 billion guesses per second, which isn't unreasonable. We're not really going to be able to measure this in years anymore. It's going to be 0 years, and they can crack that password with a reasonable amount of power. And if we give them, 1 trillion or so, they can definitely get this thing. 1 billion guesses per second isn't, if they have a server farm or at worst a botnet, and they have all of our computers, if we're infected, computing on that thing, they can definitely get to 1 billion guesses per second. 51 bits of entropy doesn't hit our magic number of 80, and it's still going to be insecure, even if you have a completely random password. So if you really want to be secure, you got to get some more length on that password, some more characters on that password. If we go up to 10, that 51 bits of entropy is going to jump all the way up to 64. And now even with 1 billion guesses per second, it's going to take them a millennium to crack that password. This exponentiation is extremely powerful. Just 2 extra characters, and we got a lot more power. And if we want to get past our 80-bit threshold, I believe 90 and 12 gets us almost there. Let's go all the way to 14. With 14, a length 14 password, it's going to take somebody quite a while to crack that thing, and we can give them 1, 2, 3. Let's give them 100 trillion guesses per second, mind you. It's going to take them 785,000 years to crack that password if you have your password up to length 14. And at 20, let's have a password generator generating random strings of length 20. They're never cracking that. They're not cracking that password ever. The sun is going to burn out before they crack your password. Even at 100 trillion guesses every single second from now until the death of the universe, they're not cracking your password. This is how fast exponentiation grows, and this is how fast we can get a lot of entropy in our passwords. But a lot of sites are afraid to go higher than 8 characters required because people won't use their site. Sometimes I won't if it's not something I'm super interested in and don't care about my security so much. If it's just some BS site that I want to go to. So 8 is the requirement, but if you want some real security, if you want to get over that 80 threshold, you got to get a few more characters on that password. Yeah?
Isn't this limited to the size of the SHA-256 hash, though? Because it's
No.
going to be, like, cut off, right?
I mean, the size of the hash is more than 20, like for that example. Yeah, but yeah, you're right. There will be a natural limit, the length of the hash. But the length of the hash is, I don't know off the top of my head. It might be 256 bytes. I don't know. But 256 bits. But it's more than what we had there. But you're absolutely right. There is a limit on that point. But whenever I was doing the entropy stuff, I said, if you have a 100% random string, the only way you're going to have a 100% random string is if you have some software that's generating for it. And even that's not actually random. If somebody can reverse engineer your RNG generation, like they can find the patterns of whatever you use to generate that. You know, there are things that they could potentially do if they really want to get. First of all, they really gotta wanna get your password, which for some of you might be true. I don't know what's the best part of the semester to have this conversation. I'll do it briefly here. Some people might really want to get your passwords, maybe not right now, but you're going to go out there, you're going to have careers where you're going to be working on software that might be used for millions of people. Your passwords might end up being very, very valuable to an attacker to be able to get a dev's password on a project that they're trying to attack. Especially if you work for a major corporation and you have some access that attackers would really like, they might want to really go after your password. So having strong passwords whenever you have some sensitive information that you have access to, very, very important to have actual good passwords. But you're not going to come up with, so that's my short version of that talk. So you're not going to come up with completely random passwords if you're actually coming up with them. If you don't have some software password manager, you're going to come up with your own passwords, and they're going to follow patterns because you have to remember it. Or you're going to write it down, and that's not super secure either. So you're going to follow some pattern. We're humans. We like patterns. There's going to be patterns to your password, and attackers are going to take advantage of those patterns. You can go online and just get a list of the probably million, I don't know, I haven't done it in a while. But you can get a list of the most common passwords, and those are the passwords they're going to start with. Those are the first passwords they're going to try. They're not going to try every single random combination of these 90 characters. They're going to go with the common passwords first. And then they're going to try variations of the common passwords. They're going to try just any words in the dictionary, which is where the name of the attack comes from. They're going to replace the common replacement characters when we need a special character, so my A's all turn into ats, and then I can still remember my password. And my password is capital P @ $$. I just take password, something I can remember, and replace some things. These are the things people do. The attackers know that, and they have their code, they have their dictionary attacks all coded up to try all these things first instead of purely random strings. Because nobody's coming up with purely random strings unless they're using a password manager. And if they're using a password manager, you're not cracking that hash anyway, so you're not even going to try. More realistically, somebody compromises a database and has all these hashes, and they're going to launch attacks on each password. With these dictionary attacks, let their attack run for like 2 seconds on each one, and then they're going to have a good long list of accounts that they have the passwords for, and then they go and attack those accounts and try to get credit card numbers and whatever they're going to do, whatever the attacker wants to do at that point. They're going to attack the weak passwords because those are the easy targets. If you have a strong password, especially if you have 20 randomly generated characters, they're not attacking you. They're not getting your password. They're getting somebody else's. Yeah?
Do these brute force attacks only happen once the database has been compromised?
Yes. Yeah, so they have to have your hash. So it's already assumed that they have your hash at this point. So step one, they have to get that hash, and then they have to launch these attacks. They can't just launch this attack right now without compromising that database. Then rainbow tables. These are scary. Not anymore, but these used to be scary. And then, now 2FA, because nobody comes up with good passwords. So now we have to all deal with 2FA, which, it is what it is, I guess. I think it's annoying, but it is more secure. If you're not going to come up with a good password, 2FA is the answer to actually get people to be secure. So rainbow tables, I might save part of this talk for Friday. Or do I save the entire thing for Friday? Can I do rainbow tables justice in 2 minutes? Nah, let's just save it. So salting is going to be the answer to rainbow tables. I'll save that whole discussion. I don't think that's on the lecture question. Save that whole discussion for next time. So when we're actually doing the hashing in your code, because it's a fun topic, I don't want to just rush through it. When you're in your code and you have to do all this hashing and password checking, the good news of this is, at least in the terms of CC 312, is that we're just going to use the bcrypt library. You're going to install bcrypt, your pip install, put it on your requirements, put it in your Docker file, whatever. Install this library, and the library does everything for you. Bcrypt is one of the things that's like pretty universally standard across the industry, thankfully. I like when things are more standardized. We don't have 100 choices for our encryption tools. You use bcrypt. You're storing passwords, you use bcrypt. Bcrypt is going to hash the passwords. It's going to handle the salts. It's going to generate the salts. It's going to attach the salt to the hash. And then that's what you store in your database. And one value which has the hash and salt. I didn't really define salt, but and then when you get the plain text password and you have to check it against the password, you grab the plain text value, you grab that one value that's stored in your database, and you say, bcrypt, is this the right password? And bcrypt happily returns a Boolean, true or false. So all of the actual hashing and checking of the hashes is 3 total lines of bcrypt, and actually one